Hello, welcome to our webinar on new geometry features in COULOMB version 9.1. My name is Dennis Peterson and I'll be conducting today's webinar. I'll begin by demonstrating the new features and then we'll have some time for your questions. We decided to do a webinar on the new geometry features because having a valid geometric model is essential to obtaining a valid field solution, and often preparing the geometric model is the most time-consuming step in a field analysis. So we're continuously working to improve our geometric modeler. So we'll show you what we've done for version 9.1. We have new methods for selecting geometry, new tools for creating geometry. We can now import and export SAT and STEP files. That's very useful. We have links to the major CAD packages, but if you're using an alternate CAD package, you can usually save a SAT and STEP, so we can read that. And we have new tools for healing CAD imports and cleaning up models. Now, if you've used our programs, previous versions, you'll have noticed that there are some changes in the geometry selection options. Beginning with version 9.1, we've removed the group selection, and we now have block and object selections. The object selection is much more powerful than the group selection. The group was limited. You couldn't assign a name to a group, so you couldn't use it in a scripting environment. And also, geometry entities could only belong to one group at a time, and that limited their usefulness. I'll begin by explaining block selections because that's the simplest of the new options. A block is simply a collection of volumes that are connected together. They share surfaces. So for example, I'm showing an insulator here which has several sections, several dielectric insulator sections, plus several plates connecting the different sections. So having a block selection option means you can select all of the insulator with just one click. And I'll show you how that works. I have several COULOMB programs open. So for example, suppose you wanted to displace this insulator or make copies of it. If you're using a volume selection mode, then you would only be selecting one volume at a time. Now you could of course try a box selection, or maybe you'd have defined it as a group or now an object. But if you didn't want to go to that trouble, you can simply change the selection type to block, and then when you move your mouse over any part of the insulator, you're automatically selecting the entire insulator. Now, named objects is a feature that we've added. It's very important, especially as we move into our scripting environment. The ability to name objects is essential for scripting. And it also increases the power for making multiple selections and classifying different objects according to their functions. The main tool you use for creating objects is the Objects Dialog Box. It allows you to create, rename, change the color of objects. And I have an example prepared to show how you would use that. So here, let's say that we have two bus bars separated by two insulators. And the insulators themselves are complex. They're composed of dielectric regions and they have plates on either end. I've already defined some objects. So I've defined the top bar as being an object, and also the bottom bar is a separate object, and the insulators are more complex objects. They consist of a number of volumes, and each one is a separate object. So there are times when you want to be able to select individual components. Perhaps you are doing a short circuit force study and you're interested on the force of the top bar or the bottom bar. Other times you might want to be able to select all the bars at the same time. Maybe you want to change their properties or to hide them. So I'll show you how to create a new object. Okay, so we'll click on Create. We have object number 5. If you don't have a name, it'll have a default number. We'll rename it and we'll call that bus bars. Now, this doesn't have any geometric entities associated with it, so we'll click on Add Volume, and we'll add the 2 bus bars. So now, the top bar is an object in itself, but it also belongs to the object called bus bars. Let's create another object called insulators. Okay, now I want to add both insulators. I could use a volume selection, but because the insulators are themselves very complex, I would have to do a lot of clicking. Since we've already defined 2 insulator objects, we can change the selection type to Add Object. And now when I click on Add Object, I could select the objects with the mouse, but you'll notice in the command line it's saying that I can also display a list by clicking on the Control plus Tab. So I'll click on Control plus Tab, and now that's opened a box showing all the named objects that already exist. So now I can select Insulator 1 and Insulator 2, select them, and right-click. And so now we have a new object that consists of both insulators. So that's very handy. Maybe you want to hide all the insulators and just work on the bus bars. Now, another example of where you'd want to create objects, perhaps you want to assign potential boundary conditions and you might be changing them. Let's create another object and call it positive. And we'll make this red. And this time I'm going to add all the volumes that are connected to the top bus bar. So I click on Add Volume, and I click on the bus bar and the metal caps of the insulators at the tops. So this is very handy if you wanted to assign a potential boundary condition. All those different metal structures will be assigned at one click. And so let's now create our last object. Let's create negative. And we'll make that blue. And again, we'll add volumes. And we'll select the bottom bus bar and the insulator sections that come into contact with that. So you can see the power of this new object selection feature. For instance, the bottom caps here of the insulators, they belong to 3 different groups. They belong to the group we just created called negative. They also belong to the object, say insulator 2, and the object that consists of both insulators. So that's something that we couldn't have done previously with the group selection mode. Now we'll move on to discussing the new tools we've added for creating geometry. We're now able to do path sweeps. We can create complex surfaces using lofts. And we have powerful new commands for merging and joining geometry. So here I'm showing an example of both a path and a prism sweep. We've had the prism sweep command for some time now. And basically, in both cases, you select either segments or surfaces, and then you select some sort of a path, which will be used to generate the sweep. In the case of a prism sweep, you're maintaining a parallel angle between the initial and final surfaces, whereas a path sweep will follow and maintain the same angle with the arc or segment you're using for doing the sweep. So I'll demonstrate that now. So here we have a surface and we have an arc, and first we'll do a prism sweep. And now it's asking for a segment, so we'll pick this arc. I don't like that direction. I want to sweep it in the other direction. So I'll hold down the Control key and I'll left click, and that toggles the direction. And now I'll left click again, and that's generated the prism sweep. And you can see that the initial surface and the final surface are maintained parallel. Now we'll introduce the new path sweep. And again, we'll do a sweep surface. And we'll select the same surface and the same segment. And this time I'm happy with the direction, so I'll just left click. And you notice now what's happened in a path sweep is that you've maintained the same angle between the initial surface and the generating arc and the final surface. They were all at 90 degrees to the path. Now, lofted surfaces are very powerful. You can create volumes with non-uniform cross-sections, which are very difficult to create in any other manner. So here I have an example. I have two parallelogram surfaces, and I have a circle which is composed of a series of arcs. So what I'm going to do, I'll define a lofted surface. Go Geometry, Define, and then define lofted surface. So now it asks for segments. So I'll pick the segments on the parallelograms, an arc segment, another line segment. And that's produced the first loft. And we'll generate another one. And finally, we'll do this one here. Okay. So you can see you can create a very complex shape by using the loft command. So now we'll move on to show how you can use the new merge command. The merge command combines separate geometry entities into one, and it removes any superfluous geometry. So in this example, I'm going to show we have a sphere intersecting a block, and we're going to combine those into one volume. So here I've just created a block, just a rectangular block, and now I'm going to add a sphere. And my center of the sphere will be 0, 0, 0, and a radius of 0.3. Now, what we have here are two separate geometric entities. They're not combined in any way. And if we want to we have two separate volumes that intersect. In fact, we can show that with one of our new geometry detection command. The intersecting volume shows the sphere in red and the block in blue, showing that they intersect, but they don't have a valid connection. So now we'll go to Geometry, Merge, and we'll merge these two volumes. So pick the sphere and the block, and you notice what's happened. The hemisphere that was intersecting the block has now been deleted, and we now have a single volume. So all the extraneous geometry has been removed. Now this is very handy, especially in the case of assigning boundary conditions to metal objects. Typically in a Coulomb model, if you're doing an electrostatic analysis, you're not really concerned with what type of metal an object is composed of. All metals are essentially very highly conductive, and they're essentially equipotential surfaces. So an example that my colleague Dr. Doug Cragen came up with, which illustrates this, is the linkage example, which you've probably seen in the update notes. Okay, so here you have a square or a rectangular block connected through a pin to another curved kind of lever or block. And these are all separate volumes. If you're doing electrostatic analysis, these would all be at the same potential. So it's handy to merge them into one single volume. So we'll do that now. We'll go Geometry, Merge, two volumes. So we'll pick first the bolt or pin and the rectangular block. And now that's one volume, you'll notice. And we can repeat the operation. The command is still active. So we'll pick this new combined volume and the curve block. And now these are all one volume. And again, I can show you using a wireframe mode the parts of the pin that pass through the two blocks have been deleted because they're not necessary. We only need the exterior surfaces. Now, a very powerful command that we've added is the join command, and this goes a long way to removing the problem of overlapping surfaces. And I'll show you that by moving two blocks into contact and showing how you can use the join command to automatically fix overlapping surfaces. So here we have our two blocks, and you'll notice that they're not the same size. They both have curved and flat surfaces, and we'll bring those into alignment. And then we'll show how we can use the join command to cure the overlapping surface problem. So I'm going to move this block from here to about here. And now that brings them into alignment. And now I'm going to run the join command. Now, what's happened here, to show what they solid with edges, I'm going to hide this block to show you what's happened to the other block. Now you'll notice that on the larger block, both the curved and the flat surfaces have been broken where they come in contact with the small block, and then those surfaces have been merged together. So again, this is a very useful command for solving the problem of overlapping surfaces. And again, I'll show you the example of the linkages. So here we have the linkages. Suppose you wanted for some reason to maintain these as discrete volumes but in contact with each other. We'll use the join command now. And you can show by reassigning materials. And let's even put a material in the bolt as well. So the main difference between the merge and the join command is that the merge command combines all of the entities into one. The join command fixes the contact surfaces but maintains them as individual volumes. Now we'll move on to talking about CAD import and healing and cleaning up artifacts from the the import. So as I mentioned, version 9.1 now permits the import and export of SAT and STEP files. We also have commands for healing surface edge mismatches, which often occur when you import a CAD file. And we have new commands for cleaning up unconnected geometry. And I'll explain also how you might want to simplify your model by cleaning up NURBS data. So with v9.1, you can open SAT and STEP files directly, and you can also export them. So that's very handy. Some of the CAD packages you may be using may not be the more popular ones like SolidWorks or Inventor. And so if you're using another CAD package, almost all of them can create some sort of a step or SAT file as well as having their own proprietary database structure. And once you've performed an analysis in our software, it's often desirable for you to save it as a SAT and step file and then open it again in your CAD package. So when you import a SAT or a step file into our programs, the program will automatically create a new object which has the original name that you saved in your CAD file. So to show you how that'll work, here I created a model and saved it in SolidWorks, and then saved it as two types of step files and a SAT file. So we'll just open up one of the step files. Oh, let's open here. Step files. Okay, and if we go to Geometry, Objects, you can see that the original name has been applied. A new object was automatically created when we did the CAD import. Now, as I mentioned, quite often when you do an import from a CAD file, because of the differences in precision, you may find that the surfaces do not quite join to the edge segments, which should be the boundary of the surfaces. This can cause a lot of problem with meshing, especially in tetrahedral meshing. You might find the program might stall because it's taking a lot of time to try and resolve that inconsistency. So to cure that, we have a new command. First, maybe I'll just rotate this a bit to show you how that edge segment here in particular, you can see it most obviously with this one, but in fact all of the surfaces here have some problems. So we'll go to Geometry, Healing, Surface Edge Mismatches. Now, its program is going through and detecting all these surface edge mismatches, and we'll just fix them one at a time. We'll enter Y for yes. And the last one was this most obvious mismatch. And so now you have the new surfaces are exactly matching their edges. Now we've also introduced tools for cleaning up unconnected geometry. Now this might occur as a result of a CAD import, or maybe as you're constructing a model, you might create reference segments or surfaces, and you may just want to clean those up in one step. So we'll show you how to clean up unconnected points, segments, and surfaces. So in this model, I created some unconnected segments and surfaces and a single unconnected point. So you can see the surfaces. Maybe I'll just show you an edge view there. The segments, the point doesn't appear in this mode. Now, it's obvious what an unconnected point is. An unconnected segment, we have some obvious examples here. This segment isn't connected to anything. This segment is connected at one point, and this segment is connected to surfaces at both its endpoints. We still consider that to be an unconnected segment. For a segment to be considered connected, it has to be part of a surface boundary. And similarly, even though this surface is connected to a volume, it's only connected on one edge. So that would still be considered an unconnected surface. So I'll run the cleanup tools. And we'll get rid of the unconnected points first. And then we'll do the unconnected segments. And finally, we'll remove the unconnected surfaces. Okay. Now the last feature I'm going to show is how to simplify your model by cleaning up NURBS data. You'll find that when you import a model from a CAD file, often things that appear to be straight lines or arcs, they're still defined as free-form NURBS curves. And for the most part, that doesn't do any harm, but it can lead to more memory usage to save all the data for the control points, and also it may cause a longer solution time. During the course of the field solution, we have to calculate derivatives. If we can do that analytically, as we can on a line segment or an arc, that reduces time and it's also more accurate. So here I've deliberately constructed a model where I broke up the segments and some of the arcs into several sections and then deleted them and made freeform curves such as NURBS. So I'll show you how that works. So geometry, cleanup NURBS data. The first thing it asks for is a length tolerance for the round-off check. So that basically is determined by the size of your view limits. We consider 2 points within, say, 1 times 10 to the minus 8th would be essentially the same point. So we'll accept the default suggestion there, 1e minus 8. And now it's asking for a % tolerance for data reduction. That takes a little bit of explaining to understand what that means. Quite often you'll have a number of points that appear to be on a line or an arc, but they may be just slightly off. So you have to tell the program what sort of tolerance based on the length of the segment are you going to allow. So for a long segment, we'll say if you're within 0.1% of the total length, then you consider that point to actually be on the segment. So we'll use 0.1 for the default. So it's found the first line. It says all of those points fall within that tolerance. So it says convert NURBS curve to line. We'll go yes. And it finds all the other ones as well. Now, you may have noticed, though, it didn't correct the problems with the arcs. Remember, I told you that I created this model deliberately by breaking up the arcs and then connected them by a free-form curve. And so these points don't quite fall within that 0.1% tolerance. So we're going to rerun that command with a looser tolerance. And we'll use the same round-off check. But now we'll use a coarser, we'll use just 1% for the tolerance. So now it's found the first arc that could, or the first NURBS curve that could be made into an arc. And it's finding all the others as well. Okay, that concludes the formal presentation part, and we'll try and deal with any questions that you might have. And I do see a question here. Okay, that's great. And it says, what format have you found best for exporting to SOLIDWORKS? I think generally the STEP format would be the best. I think STEP is a more reliable format. Oh, and there's another question here. Okay. Now it says, I have found that in 2D the block command will select both the state and rotor even though they are not touching. We'll have to look at that individual model, okay, to see what's happening there. Now, if you do find a model which is not acting properly, the best thing is always to send us a database, send it to tech support. Well, okay. Well, thank you very much for attending our webinar. And if you do have other questions that occur to you after this presentation, there'll be a recording that you can view so you can review the presentation. And certainly send us any questions. We'd like to know anything that we didn't explain clearly or anything we could do better for the next webinar. So thank you once again, and we look forward to seeing you at our next webinar.